So, what is light? Light is a form of electromagnetic, or EM, radiation, just like X-rays or infrared lasers. And what separates these different types of radiation is their wavelength. If you're not sure what I mean by wavelength, take a look at the bottom of the screen. On the far left, we see a long waveform, and on the left in the red region. And then on the right, we see a much shorter waveform in the blue-violet region. So as the name suggests, wavelengths describe the lengths of waves. Also, the common symbol for wavelength is the lowercase lambda, which looks like an upside-down Y. Anyway, all the light we can see, visible light, has wavelengths in the 400 to 700 nanometer range. White light contains a full range of those wavelengths, or a full spectrum of colors. So when we look at a white light shining through a triangular prism, like on the album cover of Pink Floyd's The Dark Side of the Moon, that white light will separate out into its components, producing a rainbow of colors. So, in light of this, what is red light? Well, you can see on the bottom, each range corresponds to a different color. So the 650 to 700 nanometer range is what we call red. In the top left, we see a white light, broken into its component colors shining on a green shirt. And on the other side, we see green light coming out of that shirt. This brings up an important question. If the full rainbow of colors is being shined on this shirt, why do we only see green? As the diagram in the top right explains, the colors of light we do not see are all the wavelengths in the visible spectrum that get absorbed, whereas the leftovers, which can't get absorbed, green in this case, get transmitted through the object, or reflected back, and then projected onto the retinas of our eyes. So that's why we see the green light coming out of the shirt on the bottom of the screen. It's reflecting back off the shirt. That last slide showed us that we only see the light that doesn't get absorbed. But what does that even mean? What are absorption, reflection, and transmission? Let's imagine that this picture of an atom, that it's really just an ultra zoomed in look at the green shirt we were looking at before. And notice there are no green electrons, but there are electrons for every other color in the rainbow. That, in a sense, is why we see green light. These purple, yellow, blue, red, and orange electrons are absorbing those colors of light. This is not to say that there are actually color-coded electrons that absorb light based on the color they look. What I am saying is that there are electrons in every atom that absorb different wavelengths of light. Some absorb in the blue range, some in the red, and when an electron is shined on by its corresponding wavelength, it absorbs that energy and transforms it by vibrating it out as heat. So, if we see a green shirt, that means that the atoms making up that shirt have very few electrons that can absorb that green light. Instead, the green light can either shine through the object if it's translucent, like a glass cup, which is called transmission, or the light can reflect back if the object is opaque, like a t-shirt, and that is aptly called reflection. All objects that transmit or reflect a certain color will also absorb a certain range of colors most strongly. For instance, something that looks red will absorb all other colors, but also absorb blue-green light most strongly. And blue-green light falls in the 475 to 490 nanometer wavelength range. Building from that table, a red ball would then absorb blue-green most strongly, right? So if we were to extend this colored electrons metaphor, then we'd theoretically expect there to be more blue-green electrons than any other color because they're absorbing the most light. Now, when we look at this picture, since there is no red light shining on the ball, no red light can get transmitted or reflected back. Further, since only light in the blue range is shining on the ball, the red ball would theoretically absorb all of that blue light, leaving only a black silhouette. Blue light in, no light out.